over 1,300 times. That's how many times our Earth would theoretically fit into the gigantic Jupiter. But while the colossal gas giant is by far the largest planet in the solar system, it still holds many mysteries for researchers. To finally change this, NASA sent the Juno spacecraft to Jupiter, which has been scrutinizing the planet, the king of our home world, since 2016. In doing so, it has brought to light a series of circumstances that are as astonishing as they are unexpected. A large celestial body means a large mystery. Although we have known about Jupiter since ancient times and it has been observed by various cultures for thousands of years, many of its secrets have not been solved to this day. What is known, however, is that the planetary giant has an equatorial diameter of a whopping 143,000 kilometers, making it the undisputed ruler in the size chart of our planetary system. In contrast to our significantly smaller Earth, Jupiter, being a gas giant, has no solid surface. In fact, the structure of its atmosphere was one of the biggest mysteries in modern Jupiter research before the Juno mission. Details like the polar regions and the magnetic field of the gas giant had only been partially explored to date, and yet this is just the tip of the mysterious Jupiter iceberg. When Juno left our blue home planet on August 5, 2011, it had many exciting mission objectives in its luggage. Incidentally, it's no coincidence that the spacecraft developed by NASA was named Juno. In Roman mythology, Juno was the wife of the supreme god Jupiter and thus the only goddess who could see through the fog that Jupiter used to conceal his affairs and pranks. From a purely astronomical point of view, however, the veil of mist hid no divine alliances but rather questions like Jupiter's origin. This should be clarified by deciphering the distribution and abundance of water, ammonia, oxygen, and nitrogen in the atmosphere. Speaking of atmosphere, since the gas giant has the densest atmosphere of all the planets in the solar system, Juno was tasked with providing extensive information about the global structure and dynamics of the gas envelope below the cloud cover for the first time. Additionally, Jupiter holds more mysteries among its colorful, almost parallel cloud bands. To gather new insights into the mass of the core, the convection currents in the interior, and the presence of water on the planet, Juno was assigned to measure the magnetic and gravitational fields. Our knowledge of the magnetosphere, which is the largest and strongest in the solar system, was also expected to reach a whole new level during the mission. So, what has Juno discovered in the realm of the gas giant? Jupiter is breathtakingly different. On July 5, 2016, after a journey of almost 5 years, Juno swung into an eccentric polar orbit around Jupiter. A few weeks later, it performed its first close flyby, passing through the gas giant's cloud tops at a distance of less than 5,000 kilometers. The information and images collected during this process once again left researchers on Earth open-mouthed because the first Juno data actually contained some huge surprises. One of these surprises concerned the polar region of Jupiter. The bands of wind that regularly sweep around the planet and give it its characteristic appearance literally vanish into thin air near the poles. Instead, we see huge storm vortices recognized as colossal spots and spirals. While the storms around Jupiter's North Pole reach diameters of 1,000 kilometers, they can be as much as 1,400 kilometers across at the South Pole. A glance at the following Juno images shows that these prime val structures are not only scientifically valuable but also have artistic merit. Although the structure initially looks like the work of an abstract painter, it's actually a purely planetary painting. The light blue areas are high storm clouds, likely consisting of ammonia ice and water ice crystals, towering above the lower cloud layers, which appear dark in the photos and even partially cast shadows. However, the fact that experts declared Jupiter to be breathtakingly different was not solely due to such wondrous images. The astounding appearance of its polar regions also played a part. In contrast to Saturn, there are no pronounced ring currents at Jupiter's poles, such as the famous hexagon on Saturn. Quite the opposite. Juno could not detect any structure that even remotely resembled such a wind pattern. In other words, the polar dynamics and atmospheric structure of Saturn and Jupiter must differ significantly. No less astonishing was the discovery of a 7,000 kilometers wide cloud that Juno identified far above the cloud cover of the North Polar region, along with thermal measurement data. These revealed that the gas flows under the cloud cover are distributed quite differently than previously assumed. Instead of a relatively homogeneous ammonia ocean, the gas at the equator forms a giant ammonia column that extends in a ring around the planet. Experts stated that the column-shaped outflow is surprisingly reminiscent of Earth's Hadley cells, air currents that transport warm, moist air at the equator and allow it to sink again as cold, dry air along the tropics. There was also an unexpected revelation regarding Jupiter's magnetic field. The data collected by Juno showed that it's almost twice as strong as previously expected and has a clumpy nature, being more pronounced in some places than others. To say that the data collected by Juno caused a stir among scientists would be an understatement. Just how radically our view of Jupiter has changed becomes clear when we listen to the words of Scott Bolton, the principal investigator of the Juno mission. He said, "The whole thing looks different than anyone would have thought before. I mean, no matter how we looked at it, we were shocked by what we saw. But sometimes, the things you can't see also cause a mixture of amazement and disbelief." Although experts had predicted a rocky core the size of Earth for Jupiter, the first Juno measurements simply could not confirm this theory. Scott Bolton was quoted as saying, "We don't see anything that looks like a core. There may be a core of heavy elements, but it may not all be concentrated in the center. Maybe it's much bigger. Maybe it's half the size of Jupiter." But how can that be? While the Juno mission initially raised more questions than it answered, it was able to shed light on other areas and finally clarify the nature of Jupiter's extraordinary auroras. They are among the most enchanting spectacles that our Earth has to offer and are also a permanent feature on Jupiter. Yet Jupiter's energetic polar lights were overshadowed by huge question marks for decades. Unlike Earth's auroral ovals between 65 degrees and 80 degrees latitude, Jupiter's don't reach directly above the poles. The unusual duration of the light phenomena, lasting several days as seen from Jupiter, also puzzled researchers for a long time. However, a few years ago, Juno, in collaboration with the European XMM Newton X-ray telescope, finally succeeded in uncovering the background of this peculiar phenomenon. After Juno plunged into Jupiter's magnetic field and XMM Newton simultaneously analyzed an aurora over Jupiter's north pole, it became clear that the auroras are actually generated far away from the gas giant. Specifically, oxygen and sulfur ions surf the polar magnetic field lines from one pole to the other. On this journey, they are accelerated in stages by a special type of electromagnetic wave, ultimately creating the typical pulsation. The corresponding electromagnetic ion cyclotron waves arise in the outer magnetic field region when the solar wind comes into close contact with the magnetic field and compresses it. This releases energy, causing vibrations and catapulting the ions back to Jupiter in spurts. At the end of this process, the incoming particle storm triggers the glow of the auroras. According to experts, this fundamental spectacle could also be significant on other planets such as Saturn, Uranus, and Neptune. As briefly mentioned earlier, deciphering Jupiter's origin is also one of the overarching Juno mission objectives. To understand how and from what the gas giant formed, it is essential to examine its chemical composition closely. That is exactly what Juno did when it studied the cloud cover of the Colossus at close range using its microwave radiometer. Jupiter's cloud-filled atmosphere does not primarily consist of water vapor or water ice but of frozen ammonia and ammonium hydrogen sulfide. Yet, there are also clouds of water ice here, more than previously thought. While the measurements of the Galileo mission indicated that the gas envelope of the planet contained far less water than assumed, Juno's observations showed that Jupiter's atmosphere, at least at the equator, contains much more water than suggested by previous data. Since water in the reflected microwave radiation leaves a specific absorption pattern, this also provides insights into the overall water content. In terms of numbers, this means that the water content in the equatorial region of Jupiter is 2,500 parts per million. To put it another way, water makes up around 0.25% of all molecules in Jupiter's atmosphere. If these measurements are representative of the entire planet, its atmosphere would contain 3 times more water than exists in the Sun. In view of this surprising finding, Scott Bolton once again expressed his great astonishment. No sooner did we think we understood Jupiter than it reminded us how much we still have to learn. But what can these values tell us about the formation of Jupiter? According to the current theory, the gas giant was the first planet to form in the primordial cloud around the young Sun. In the process, it incorporated a large part of the material in the accretion disk. If Jupiter formed through a partial collapse of the primordial cloud, its elemental distribution should correspond to that of the Sun and the rest of the primordial cloud. However, if the planetary core formed through the gradual accumulation of smaller chunks, these could have carried more ice and thus more water. Some formation models can already be discarded based on the new Juno data, but before we can draw a comprehensive picture of Jupiter's birth, a little more patience is required. As already mentioned, we still don't know whether the water content of the equatorial region is representative of other areas of the planet. To clarify this, Further on-site measurements are essential. The good news, however, is that Jupiter's successor mission is already on its way. If all goes according to plan, the ESA probe JUICE will reach Jupiter in July 2031. Once there, the aim is not only to further decode the gas giant, but also to determine whether the Galilean moons, Europa, Ganymede, and Callisto, are habitable. And our probe has found out that the subscribe button is definitely clickable. Click now on the thumbs up and subscribe to never miss a new video from us again. We'll see you soon.